Okay. All right, let's get started. I posted, I wrote these in office hours today. There very well could be mistakes. We'll figure that out as we go. But yeah, huh? I meant to post them after office hours, but I got into conversation with a student from last year. But I posted them like 30 minutes ago, probably.
Okay.
But I'll write them out. So first we'll do 8 examples of potential questions for specific example reactant reagent product. The first is a viable mixed aldol. So viable mixed aldol means that you don't get a mixture of products. So we want to have something that has acidic protons that you can use as a nucleophile and something with no acidic protons. So something with no acidic protons, that's an aldehyde, could be benzaldehyde. And then I'll say, using acetone as our other, we can get, so aldol condensations are catalytic with methoxide, not one equivalent. The acetone is our nucleophile, so that's what's going to keep a carbonyl, and the other one will be an alcohol. So that is a viable mixed aldol. This could also be a T-butyl. You just need the aldehyde proton here is not acidic, and there's no proton there. You just either need no proton there or that.
Could you do like a O double bond to a C and like HH?
Like formaldehyde?
Yeah.
Yeah.
Could you use a carboxylic acid instead of aldehyde?
The carboxylic acid would be deprotonated by the methoxide.
Is the polymechic for it?
Because you can't deprotonate anything here.
Okay.
What
So
about
just
an
want to
amide?
have that.
And then this is symmetrical, so you can't get a mixture in that way.
That's like never I thought.
Could you do it for amide? Amines?
That's like contemporary aldol chemistry where you use LDA.
So like you can't do an aldol with irreversible conditions with an amide?
You can't do an aldol in reversible conditions with an amide. Well, also the amide pKa is 16, so it could be deprotonated by the methoxide as well.
Okay.
But aldols are typically referring to condensation of aldehydes and ketones. Did someone else have a? Sam, did you have a thing? Oh, you had a thing?
I was just wondering if, like, does it have to be an aldehyde that's connected to it? Like a benzyl?
Well, if you did a ketone, you would get a mixture, but also ketones are less electrophilic. They're not as reactive with nucleophiles, so the reaction isn't as good. The aldehyde is a lot more electrophilic. So that's viable mixed aldol. And then at the bottom we have the 4-product aldols, which Kayla was just talking about, which we can look at. Claisen condensation, this is like an aldol but with esters, and you don't get an aldol product, obviously. You get a ketoester. So I'll just say 2 methyl acetate. This we need 1 equivalent. Remember to use the methoxide of whatever product you want. Like if this was an ET and I had an ET in the product, then I would use sodium methoxide and ethanol. And then ammonium chloride. Hello. That's Claisen condensation. I also didn't write down any answers to these, so I'm hoping that I remember. Well, I can figure it out, I guess.
Can you do decarboxylation on it in like a synthesis?
On this?
Yeah.
Yeah. It wouldn't. Yes, you can.
Okay.
That would just be H3 plus some heat and get there.
Sorry. What other nomenclature do we have to know other than amino acids?
Amino acids, amides, I think you were tested on last time, right?
And then
And then what?
and stuff. Right?
Yeah. So probably just that. Nomenclature-wise, amino acids will probably be the thing. A Dieckmann is a Claisen in a ring. So let's see. 1, 2, 3, 4, 5, 6, 7. Same reagents as this.
So Dieckmann is just Claisen and internal.
Yeah. Yes. I mean, it would,
Kicks out the methanol,
yeah, it's, you need a full equivalent here, so you get a methanol. You don't need to put byproducts for specific example.
Is the one equivalent just because if you have more than that, then it's going to start doing some funky stuff using one product?
The one equivalent here is because in the mechanism, whenever you get this product, but then it's going to get deprotonated by the methoxide that you regenerate up to that point. So you need to then use ammonium chloride, because this pKa is 11, methanol has a pKa around 16, right? So this is going to be favorably deprotonated, and that's resonance stabilized, so it's not going to pull off a proton off of another one of these, because this pKa is 25. So you need to have a full equivalent when you're running the reaction, then you add acid at the end to protonate that to get your product, so it doesn't separate out. Does that make sense? Okay. Reductive amination. Ketone or aldehyde here. Do you want to put the amine? The amine that you have will replace the oxygen in a sense that the product is this. So you need your amine, you need sodium cyanoborohydride to reduce the aminium. Methanol is the solvent, and pH 4.5 so that you can, I believe maybe I put a reductive amination mechanism somewhere in here.
Where does the methyl come from?
What methyl?
On the amine.
This?
Yeah.
This is the amine that you add.
Oh, yeah, wait, you're right.
Yeah. pH 4.5 is so that you can do two, what's the word for, two sequential protonations of the, in this case it would just be to get a water group that you can pick off.
Is that reductive?
This is reductive amination, yes.
Booyah.
Okay, a Michael addition. Michael addition can mean a lot of things. The one that you had on your bonus problem set was with the acrylonitrile. I'll just do.
Is that first name in the reductive amination, that's the thing you can change, right?
Yeah.
You can just slap whatever you want.
Yeah. So I could make it.
Ooh, is this what we're doing
I was going to, but I didn't want to have to.
So that would
Right,
be
try.
That would be ETOH, right? It would be methyloate or ethyl.
No, you can still use methanol here.
Okay.
So Michael addition. Here you're going to use some dicarbonyl that you'll deprotonate and use as a nucleophile to do a conjugate addition, right? So which I guess let's use methyl vinyl ketone. And so this carbon forms a bond to this carbon. So that's that carbon now. This one, this one, this one. That's a Michael addition.
I think it just has to be about
But that also, I don't think it has to have a ring composition.
Yeah.
Which one?
That would form an internal.
Like here?
Yeah.
Like you could drive that, but it would be different reaction conditions, but this can work under other conditions. I'm not sure exactly what the change is, but.
Does it just have to be a dicarbonyl, or do you have to have
Yeah, some kind of dicarbonyl, or these can even be nitriles
do
instead.
you have to have that oxygen on there then?
This, no.
Okay. That's just for funsies.
Well, yeah. I mean, this is, yeah, it's for funsies.
Can you do an example where it's because there were a couple that form like 2 rings or something?
The Robinson annulation. Funnily enough, that's the next example. So Robinson annulation is, yeah, John.
This can go later, but can you explain what do the reagents do in placement? Like, because the rest are catalytic, in for Michael,
Yeah. The one equivalent, well, the methoxide just deprotonates this.
okay.
So you get an enolate, and that enolate attacks the carbonyl of this one, and then you kick out the methoxy.
And then you can attach the second thing.
That attaches the second thing. That gives you your product. The reason you need one equivalent here is because the product that you form is acidic. This is a pKa of 11. So the methoxide that you make when running the reaction will deprotonate that again. So you need a full equivalent in order to run the reaction.
Okay, I wasn't sure, but since the methoxide was adding somewhere.
If the what?
The methoxide was adding on to somewhere, but it's not.
No, it doesn't add. It turns into methanol during that part of the reaction. And
Okay.
The Robinson annulation just makes the
so Michael addition. The Robinson annulation is a sort of specialized Michael addition. It's like a Michael addition plus what?
With an internal label.
With an internal aldol E1CB. Yeah.
How do you spell that?
Which one?
The Robinson.
Robinson. I think Robinson we're good on. Like
Yeah.
spelling. Okay.
No, you need to spell that.
That's my best guess. I got a Christmas sweater this year that says, like, I'm an engineer, but it's spelled wrong and crossed out. I'm an engineer, crossed out. I'm an engineer, crossed out. And it says, I'm good with math.
If that prototyping reiteration.
Okay, Robinson annulation, let me think here. We're gonna, what'd you say?
No.
Oh.
That's it, shit.
So again, we need a dicarbonyl. And then we need another, let's just do it with this one. We need, wait, 1, 2, 3, 4. Yeah. Yeah. So, for Robinson annulation, we're just going to smush these two things together. And we can do the mechanism. I think I put a Robinson annulation mechanism in there. If not, we'll do it whenever we come to it.
I know what happens.
Okay. That's probably the simplest one you can do.
Wait, does it matter which one?
Yes.
It's the same.
Okay, so it does matter where the double bond goes because this deprotonates. This is our nucleophile. This is a pKa of 9, so 9 is a good nucleophile. Does a conjugate addition. You protonate this side. This you form an enolate here. You protonate that side. Again, we'll do. I can write out all the steps. Did I put one on here?
Actually, like,
I might know. Maybe I didn't. Is now a good time to just do it? Okay.
Wait, so what's the difference like this and a aldol condensation?
It's just a different. Yeah. I mean, there's an aldol at UNCB that ends this reaction.
is a longer reaction that contains both a Michael addition and a
Yeah, I do not.
reaction.
Yeah.
It's sort of combined the two.
Yeah, there's not this
do
mechanism.
we have a mechanism like this?
Not in the
Because it
thing.
sounds like an extra long.
I think
This
it's
one.
right.
I
It's
think
just
the way
two
you got it
reactions
is
in the same one.
It is long.
I think you can
Yeah, so I just need to combine,
We're a very opinionated crowd today.
I just combine it into.
Okay, this deprotonates.
Some of us have today, so we're doing
Let's see if I can fit this whole thing in here.
I believe in you.
So there is the deprotonated dicarbonyl. What did he say?
You have.
I said I was gonna deprotonate in between his carbonyls.
Okay.
Yes. I second this.
Okay, so we've deprotonated. That's how, I know, I'm thinking about how there's only, what, 2 weeks left and that's.
Hello.
No, okay.
Greener pastures are gonna miss me, Brad. Yeah, you're gonna miss me. Okay, you can text me on Instagram.
Conjugate addition.
These are all like fire.
I'm drawing this small because there's.
What if I text you?
Am I missing a carbon? Yeah.
If you have a big B3,
Someone remember Exactly.
This has gotten small already. All I did here was a conjugate addition. It's not the prettiest, but. So then we protonate the one side. And this is something that is kind of like a recurring theme that you should remember, even for like doing retroaldol aldols, that you'll end up with an enolate on one side, you protonate that, and then deprotonate the other side.
Oh, yeah.
That's a pretty common thing to test for. I'm gonna, whatever.
What's this kitty? Oh, okay.
So there we've done a Michael addition. This is the same mechanism as that, just with a ring. Do we see that, how it's the same?
Yeah.
Yeah.
What's the same? These two things, can you just like move around?
This is that, no, Michael, it's Michael. He's saying BCR is Michael.
Where do we differ?
Oh, you mean the first
Are we not different
You
yet?
have all of this.
We're not there yet. This is the Michael addition.
Because we have something else gonna happen.
Well, that's what
So now I'm deprotonating the other side of this ketone. That's fine. I was gonna.
I could. It's a 50-50.
Okay, now we're gonna attack this carbonyl. So in that we form the ring, we have an O minus here. I'm gonna protonate this.
I look at it. Like, I refuse to. Yeah, not anymore. You should send like, it's still in your file though, so you can take.
This is like.
Yeah.
Is the bonus items even to be on the test? It's just like bad stuff.
Probably not. Now that I'm readying up, but
Like half of it.
but half of it could be. Or something that's like it.
Yeah, they just moved over, it's fine.
Just remember sometimes it's like.
Okay. So now we have our conjugate base. This is the part that's driven really by the heat, because this is still an acidic proton, but you will pick it off.
You're doing one step around, so.
No.
All of it.
This is the kinetically the slow step. That's the one that's like rate limited
Yeah, actually.
to make the conjugate
Like, I
base.
can't deprotonate and
The
then
bottom
have it make a double bond.
Just like like do an elimination with a hydroxide.
Yeah.
No, show it as two different steps.
Wait, yes, yes.
I mean, you can if you could if it was like a bromine or something, but OH is a really bad leaving group.
No, so I have to show the step where there's a carbo. That's stupid.
Dr. Funkich showed it a different way.
Yeah, he didn't show it like that.
Did he show it as an enolate?
He like switched the hydrogen off and then attacks the double bond oxygen.
Let's go back to QAM 1 of 210H. This is just a resonance structure of the enolate.
But, like that like stresses me out that I'm not doing it right.
I'm resonating.
I'm resonating it.
Why would about we progress?
Do I have to draw the resonance structure like that, or can I draw the enolate?
They're resonance structures. Neither of them exist.
Okay, but like, can I draw the enolate?
Yes.
Like it doesn't matter from
I'm
there.
about to draw it. It's just a resonance structure.
So it doesn't matter.
So I can.
I just like need to know if like that's okay.
Yes.
Okay.
Could I also just like turn it into water and then do E1?
Turn it into water?
Or like the, no wait.
Like protonate it? You're in basic conditions.
But it's heated up, so like.
But it's heated up. Oh. My bad. Forgot. Wait, I wanted to see.
That's a classic mistake.
Okay, I'm going to make one modification that I was thinking about.
So all this?
Well, it's one modification. I'm just gonna.
Oh my God.
I'm just gonna turn it into a methyl. It's just gonna be a methyl.
Yeah, that's it.
Why are you doing that?
Because then it's not acidic.
What are you talking about?
Like, would this do something that we don't know? Or don't
Well, I mean, the problem with that is, huh?
You talking about like
That not having a methyl means it's more acidic than this, and you're not probably going to create the dianion.
So we need a methyl.
In my lab, I created it.
You created it
Yeah, in my lab.
without the methyl.
Yeah.
I'm confused. What did we do this?
I'm just putting it there to be more precise because this probably will run better.
Yeah. You're not IRL lab.
But you did it? Did you create that product without the methyl?
No.
Well, I thought you said you did Robinson annulation as a synthetic product in
I'm
213.
talking about in my notebook lab.
No.
It didn't have that methyl, would it just have that?
Yeah, that was my bigger concern was that there would be no preference. Guys, I'm so tired. I really can't do with all the extra talking.
Sorry.
Thank you. My bigger problem here was if that methyl was not there, then you could also deprotonate here and have an elimination, make an alkene in the middle. Go for it. Okay.
Wait, it's done?
That's it.
Why doesn't the... Why doesn't the double bond take the H from the methyl?
What? Why doesn't the double bond take the H from the methoxide?
Well, yeah.
Like this?
Yeah.
This is going to here. This is eliminating the OH.
Well, yeah. But you have in the one before you have a CH3O minus taking an H.
Yep. That deprotonated it to make this enolate?
Correct.
Are you asking why the hydroxide doesn't do anything else, or?
I don't know, really.
Well, what part, it's which step? This one or this one?
Well, it's just like, why is there a double bond at the end of one, isn't it?
Oh, because you've pushed this here, and then you moved this moved this moved this double bond here and kicked off the oxygen. The carbon still needs to have its 4 bonds.
Okay.
It's like doing an E2 with potassium tertiary oxide, where you deprotonate and then kick off the bromine and form that double bond. This is just an E1CB where you kick off the hydroxide and form the double bond.
Okay.
Maybe. Sorry, I realized I was a little aggressive with telling you guys to stop talking.
It's valid.
Yeah, that's our fault. We take full accountability.
I feel like you're not mean enough sometimes.
Okay.
Call me dumb, bro.
What? Are you?
When did the cat invent?
Okay, well, here you turn this into methanol, but then you also make hydroxide, so that's just an equilibrium. You have something with the same pKa, essentially.
Okay. Where's Nick?
Yeah. Five proteins.
That's low.
5 mechanisms.
Balance on both sides.
What's up next? Oh, Hoffman. Okay. So a Hoffman is a way to create amines from amides. Here you need 2 equivalents: sodium hydroxide, bromine, heat, and this will create your amine and CO2. The CO2 you don't need to write though if this was a reactor reagent product. How this works. That's not. Deprotonate. I'm just going to write the N minus. We deprotonate the amide. Then we attack bromine. And then we're going to deprotonate this. This is where the other equivalent grade comes in of the hydroxide. We use the first one here. We're going to use another here. And I'm showing this one. I showed this one as the minus charge because that, in this case, the nitrogen is really the nucleophile. Well, that's where you're adding on the bromine. Here, we are going to. This is the rearrangement step. We get to use our fun arrow. This comes down.
And that thing flies across the entire molecule.
Yeah.
Yeah.
This shifts over to the nitrogen and kicks off the bromine. That all happens in one step, right?
Yeah.
Yeah. Okay.
When you're looking at this on the test, this is not possible.
So we've moved our alkyl group onto the nitrogen. This is an isocyanate. You can get the same thing. Well, no, never mind. The other case where we see isocyanates is with the Curtius rearrangement. That's just from acyl azide and heat, and that gets to the isocyanate. So we've made water in here. The water is going to attack. This part of the mechanism, I would say, is less likely to be on the test. So I'm going to abbreviate part of it. Um, there's 2 additional steps here to do proton transfers. Just gonna skip over that.
No.
No? Okay.
Just this one time.
No, yeah, I mean, it's fine.
Thank you so much.
Deprotonate that. And then protonate this. Acid or water, I mean, at this point it doesn't.
Is the one with sodium azide the same, like mechanism-wise? Not like, except for the first part, of course. But like after the...
Yeah, I mean, yeah, once you generate the isocyanate, you can react whatever. Yeah. I'm saying hydronium here just because I used water to deprotonate it, but if there's still hydroxide left over, you can protonate it with water. So this is our carbamic acid. So actually, I'll draw this part bigger. Carbamic acid. Here we're going to do the little dance with water. A little weird. Where water acts as a catalyst. Because you use water but simultaneously regenerate water. What's up?
Sam can't see, so he's
I, yeah, I took my contacts out.
Do you need to come up?
I don't, it won't help.
Okay.
Why'd you
So this deprotonates the acid part of the carbamic acid. Push that here. So in doing this, we've deprotonated this. This bond's going to here. That's CO2, but we have this extra bond. We don't know the pentavalent carbon. So that's going to pull off this H. I'll do that one more time.
I'm looking.
It doesn't go into the nitrogen?
It does. I'm just saying the electrons that are coming off of here are getting.
I see the vision. I see the vision.
Yeah.
Can you do an extra step where you have it where the negative charge is on the nitrogen and then it deprotonates on water?
Negative charge isn't going to end up on the nitrogen.
Yeah. I thought the negative charge went to the nitrogen first and then it deprotonated.
Then
the
where does
water.
the other hydrogen go?
Oh, that's stupid.
Okay, let's restart. This is all happening kind of at the same time. I mean, if you wanted to show maybe this deprotonating and get an O minus here and then doing that part, but I wouldn't show it kicking off like an N minus. Although, I mean, it doesn't matter a whole ton.
Okay.
This water deprotonates the acid part. That moves this bond between these 2 carbons. Now we have CO2, right? Since we've just formed that bond. We can't form a pentavalent carbon, so this bond that belongs to the nitrogen goes and deprotonates the other half of the water. So water has gained a proton and then lost a proton, so we're just back at regular water. So that's why water is acting as a catalyst here. Yeah.
To make that starting amide, could you add NH2, NH2 to an acid chloride with the functional group on the left side? Like to make
Hydrazine? And you would just add ammonia
just add ammonia. Okay.
to an acid chloride with the, yeah.
Okay.
Where's my, yes, Maureen.
So it's like kind of an off-topic question, but do you know you can do like atomic all-night or whatever, the Gabriel synthesis?
To do the Gabriel synthesis, yeah.
Yeah. Doesn't the sodium azide use
Sodium azide so you use sodium azide on an acid chloride, and that would make that. Then with heat, you go to that. That's the courteous rearrangement, this part. But that's just a different reaction.
And then once you get to that part, what do you do after that to keep going?
Once you get to this, that's the end of the courteous. You just make it isocyanate. You could add water to it then to make the amine, but it's just a different way to get isocyanates because they're used in all kinds of different applications. Lots of paints, or at least resin synthesis. Blocked isocyanates too. I can't. I have a meme that I want to share, but I'll withhold because it's already 8:45. Aldol E1CB. We already did an example of an E1CB over there.
This is what I was talking about when I
Oh.
explained. So like this reaction
Yes, the Gabriel synthesis.
versus this one.
This one you use LEH, so this is just a two-step synthesis. It's from an alkyl halide to the.
But it does like the same thing.
Yeah, you're just starting with a different.
Yeah, it's just a different thing because you're still using like an alkyl halide.
Yeah.
Okay, so it just does the same thing, it's just different ways to do it.
Mhm.
Okay.
Okay, aldol E1CB. I'll do this one as let me think. 1, 2.
Oh.
Wait.
No, don't think that way.
No, it's okay. It's not a problem. It's okay. But I'm just gonna do
Aldol E1CB.
That's catalytic specific.
Deprotonate the ketone, attack the aldehyde, and then protonate that, deprotonate alpha to the carbonyl, and then kick it off.
What are the odds that like cuprates or whatever?
That who?
Cuprates? Because that's
Cuprates?
on the synthesis and all that.
Oh yeah, I mean you could cuprates are totally fair game. I mean you could use this and some that could be your starting material, and then maybe you do tandem vicinal difunctionalization there, or you know, even like maybe you have a Novanagle that you do, and then you do with a cuprate.
Two questions. Does it have to be a ketone and an aldehyde specifically?
For an aldol E1CB, but sort of yeah.
Okay. And then does it have to be an internal, or do you can have two? Like something?
You can have two.
Okay.
I did it internally, and also it can be two ketones again. That would just be slower because the ketone's less electrophilic. Oh no! Wait a minute. Plug in. Yeah.
Did you try the Maribel?
I actually already ate both of them. They were good. Thank you.
Which one was better?
The chocolate one.
What's your rating instead of that?
You probably want to see. I think they're better than like the Gatorade ones. Let me move this there first.
This is like one of the best ones you can get. We balled out for
No, yeah, I do appreciate it. It was good. Since we're not even done with page 1 yet, I feel like I made this practice too long.
I think this is, it's kind of like all encompassing at the beginning.
Yeah.
Just get the easy one first. Okay, 4 products. The 4 products that you make from an aldol and then from a Claisen. But honestly, yeah, this first page is, if you can do all the mechanisms and everything like that, you're probably in pretty good shape. But so this is a mixed aldol that will give you 4 products. The 4 products will be in varying amounts depending on how good whatever you deprotonate first is as a nucleophile. So let's say first I'm just going to call this one A and B, then I'll make the mixtures of them. Let's say that you deprotonate A and attack another A. You will get that. Let's say you take A and attack a B. Don't attack bees though, they're useful pollinators.
Hello, just attack bots.
Say you deprotonate B and attack A. And then B and attack B.
Wait, why does the methyl group go down?
I mean, as opposed to going up.
I don't know. Like, why does it start going down that way, but the other ones don't start like that?
Like these ones you're going this way? It's just for like space to write it out.
No, that's.
Like I could also write it like, here's the original, and then, what is this, B to B? Like I could, it's just a different confirmation.
Like, why isn't the methyl group going down and like AA and AB?
Because this doesn't have a methyl. It doesn't have an extra methyl.
Oh.
This is what you're deprotonating. You make the enolate and use that as your nucleophile on the other thing.
It's clocking now.
I'm glad.
Wait, so.
Yeah.
No, that's not what
And then the same thing, but esters for Claisen. Except one equivalent. And here, it's going to be the exact same set of products, except it'll be a dicarbonyl, and this H will be an ester for methoxy group. So this is A to A. Here's A attacking B. Here's B attacking A. And here's B attacking B. Exactly the same set of products, except it's a dicarbonyl because you kick out the methoxy. And this H is replaced with the methoxy from the ester. Yeah.
Just to confirm for that first one
Mhm.
on the left, if we added heat to that, those OHs would get kicked off. Or those OHs would turn into,
Oh, on these?
yeah, those would turn into carbonyls.
Yeah, it's a little bit, E1CB works better whenever you have a better conjugate base. So, like for Novanagle, that's kind of like an aldol E1CB, but it just has a different reaction name. That's a better E1CB because the conjugate base of the dicarbonyl, the pKa of that is a lot low, well, 5 orders of magnitude lower than an alcohol. So those are the, and whenever we looked at, I think E1CB in the first semester, he gave an example, I think, right? We talked about that. That example probably was a dicarbonyl if you like look back at your notes and see what it was. Those ones work better. So.
Oh, so if we add heat to that, it would just turn to like a Novanagle where there's like a double bond onto it.
Like if you added heat to this one, for example, you could maybe get this.
Yeah, okay.
It's just a little bit, it's,
Unlike the
it won't work as well as the dicarbonyl things. Okay. Next, we want the 2 iminium ion intermediates that you generate And that. The first aminium this will then, the sodium borohydride, sodium cyanoborohydride will donate the hydride here. And then the second one is there. So after you reduce this,
Is the hydrogen on the first
oh, yeah, good catch. Yeah, so then after you reduce this, you have another amine here that you react with that. And that's
What was this question?
That's the reduction step. Make sure, I have a feeling, again, I haven't seen the exam yet, but I have a feeling something, at least a part of reductive amination would be a mechanism to ask. Make sure that you show it like this and that you don't show a hydride doing like an SN2 with a water group or something. Okay. So next we have glycylalanine. The part with the eel is going to be from the N terminus. Glycine is achiral, has no R group. So that is the part for glycine, and this is the amide bond.
Oh yeah, there's no stereochemistry. That's so great.
No, there is stereochemistry on this.
For glycine, for glycine.
Oh, for glycine.
I drew the stereochemistry for the hydrogen.
Yeah. Alanine just has a methyl.
Is that the right?
Where's the opposite?
Oh my goodness, I forgot. You forget 1O.
Yeah. Is that the right stereochemistry?
No, you can't make mistakes, I think it all wrong.
I think so. Wait, it should be, yeah.
I thought it was facing backwards. Am I dumb?
That's right, stereochemistry.
Okay.
S. I mean, you may have drawn it. If you draw it backwards, then.
I drew it like this.
Oh, with that being dashed? Or?
Yeah, the
Okay, then this is first priority, this is first priority, second, third in the back of the hydrogen's coming front, so we flip it.
Okay.
Thank you. Okay, conjugate acid, guanidine.
My favorite. Never mind.
So this one is quite basic with the proton, which unspecified proton where it came from. It's just asking to draw the conjugate acid of guanidine and two resonance structures. Yes.
Are we gonna need to know like exact pKa's?
No. Like you won't be asked the number. You can be asked to compare and rank, yeah.
Oh, right.
But if it's a ranking one, it'll be, you can figure it out based on like the theory or like a comparison of them more than needing to know a specific number. And then lastly, okay. Next up, starting on the box problems. Where are the rest of my? Okay, here's an azide. You don't need to know the mechanism for this one, but know that you can reduce azides to amines using LAH. I feel like your head is going to hurt so badly, Sam.
No, I'm just trying to like maneuver my eyes to make it.
Maneuver my eyes?
Yeah, I'm trying to like poke them into the right shape.
I think that's how that works. I got muscles for that.
That's the box. No mechanism. So, second box problem. It's like algebra. 2 of what with? Oh my god. Not Clayson. Not Michael.
It's just cell actions.
Aldol. Yes, great.
We covered all the reactions we need, like, for those first eight.
I mean, there's others.
Like last.
Yeah, there's like other things, probably like smaller details, but those are the ones that I would, if there was like a give a specific example, be those. But like this wasn't on there, you know? Courteous wasn't on there. Oh, we didn't talk about quad ammonium salts at all. How much did you cover those in class?
For like 5 minutes.
For like 5 minutes. We'll squeeze it. I mean, it's like you probably use them as an example for how to, for like maybe precursor to the Hoffman elimination. Like maybe he showed it right before showing what the Hoffman elimination was, right? Let me think.
Is he gonna do a triple box?
Yeah, well, wait, let's do,
In visual 11.
Wait, that's kind of troubling. I don't want to like. I don't want to skip out on something that could be asked.
She's never won.
Okay, I'm going to add another mechanism in, just so you can see an example of the quaternary ammonium salts. I'll write that.
You say that. You have green on your list.
I just wrote a big quat, so I can remember. Okay, so this was like the aldol one that we did, the 4 aldol products, except there's only 2 here. The aldehyde is that. Okay. Next we have an ester. LDA first, semicolon, an aldehyde, semicolon, water. So we have the semicolons here so that you don't get a mixture of things. You add the LDA to deprotonate all of this, make the enolates. Then you add in your aldehyde. It attacks the aldehyde. And then you work up with water. Yeah.
Why are we doing water? Why don't we just do methoxide? Why are you switching up?
Why are you saying
It doesn't. This is really. You could put methanol there if you wanted.
Okay, but like this is like the same.
Well, but this was selective. This way it only does one of the versions.
Right. Right. If I added methoxide and had the aldehyde in there with it, it will attack the ester and kick that out. Here, the LDA is not going to. Like if you have methoxide, the methoxide might just attack here, and it might not deprotonate this as well. This is a stronger base than methoxide. So it'll deprotonate this, you add in the aldehyde, and you'll get one product here.
Was that a quaternary ammonium?
Huh? It's not. I said we'll do that later.
Oh, okay.
Okay. Okay, I made this question, but I feel like I should have written it the other direction. Because it's just heat, but I'm realizing now that I should have just put it in the forward direction. I was writing these quick in office hours, I don't know.
Heat. I see the visions. Wait, no I don't.
Yes.
There was a different.
Courteous, indeed. You can tell by the N2 byproduct, I guess.
Jump off the building.
Dude, I'm just so many right. Like I gotta
It doesn't matter what resonance we draw in, right?
Nope, because its resonance structure doesn't exist.
Ah, you're right.
It exists in my heart.
It does exist in my heart as well, I'm glad. Okay, so that's courteous, and that is the end of, let's say, the page 1.
That's only page 1?
How many pages are there?
4. but they're things.
We could do a sleepover. Okay.
We're making progress. We're making progress. Okay.
Yeah, it's so,
This is the same time having this semester.
and it happened like last semester
Yeah, this is
too.
why I didn't get skating track.
Okay. We have a ketoester and a ketone, methoxide, methanol, and heat. Do you have a question, John? I thought you said weight.
No, I said wait because I didn't want to see the answer. He said wait.
Wait, are
Okay.
these mechanisms or boxes?
These are boxes.
These are boxes.
This is brain fun.
We all know what
How
this
many more
is.
boxes do you have for spacing?
Is this for like organization?
3 more regular boxes, 2 double boxes.
We could do it.
Okay, this is a Novenagel. The heat gives that away, kind of. This is the more acidic thing. So this gets deprotonated, pKa of 11, deprotonated, attack the ketone, O minus, protonate that. Then, whenever you have this is an intermediate, okay? When you have this, this is 5 orders of magnitude more acidic than this OH, right? So this is going to get deprotonated. The heat will kick that off. That is the Knoevenagel.
How do you spell that?
Because you kick off the
It is. See, you're seeing that they're all the same reaction. They just have different names because they're in different contexts.
Wait, so how is this one different than that one?
How is it different than what one?
Aldol condensation.
The aldol U1CB. Mechanistically, it's the exact same. Just this is how the beta ketoester. That one was just a ketone or something. Yeah. Is that your question, Marie?
Oh, I didn't have a question, I just can't see.
Oh, sorry.
No, that's not easy, I'm just short.
I got you. How are we doing?
So I'm gonna destroy the mechanisms.
Yeah.
Yeah, you said
Hopefully we'll not.
You said yeah.
Okay. Next we have 1, 2, 3, 4, 5 carbons. This is the same reagents as that one. Here, though, it's not a Novenagel, it's an internal E1CB, aldol E1CB.
You all do this one?
Deprotonate here,
Yeah.
attack here,
Yeah.
O minus, deprotonate the O minus, deprotonate adjacent, kick it off with heat.
Yeah, I like that. Yeah.
Did you, yeah, Alyssa?
It's like a really dumb question, but what's the difference between aldol E1CB and aldol condensation?
Aldol condensation is this. You get an aldehyde alcohol.
I don't think concentration is really bad.
So condensation in this sense is just referring to condensing, turning two things into one thing. When we think of like in a biological sense, a condensation reaction loses water. It doesn't have to lose water here. Okay. Next up. We have, this is kind of reminiscent now of a viable mixed aldol, except here we have an ester, because this has no acidic protons, right? So with methoxide, and we need one equivalent here. The only thing that you can deprotonate is this ketone. You make the enolate. This enolate attacks this carbon. Then you kick off the methoxy. Sorry, wait.
Wait, does that just add to the ring?
Yeah, wait, I'm trying
I think it just adds to the ring.
to, where does the minus charge go?
Yeah, I think it's just like, it's just chill.
No, something's wrong there.
But it's still like an aldehyde.
Duh. Yeah, you're right. You kick out the methoxide, not the
Yeah.
proton. Yeah, sorry. So, deprotonate. You deprotonate, get the enolate, attack that. Then your intermediate, the important intermediate here. Thank you, Greg. Get this tetrahedral. What's that? Okay.
We're just talking to ourselves.
Do we understand that?
Yes.
It doesn't really have a name, I don't think. At least I don't know the name. I'm gonna put 2 arrows because this will again have this step where you deprotonate the product and then protonate it with the acid. But this is the important step of making the aldehyde there is because you kick out the methoxide.
How many points would it take off if we just like don't do the 2 steps and then just do the first?
In a mechanism, you'd probably lose 1/3 of the credit for the mechanism. Because I think there's 6-point questions, or are they 8-point?
I think that's
If there's 6, well, I think it's 24 points, and I think there's 4 with 1 omit.
Yeah.
So I think they're 8 points each. So you probably lose 2 points for not doing them.
So the one that's 1 equivalent condensed semicolon acid, that's, is that Claisen and Diekmann?
Claisen and Diekmann, yeah.
Okay.
Basically, it's the condensations where you end up with a dicarbonyl.
In its way, we get rid of like a methoxide.
Yes.
So when you add the chloride ammonium thing, is
Yeah.
that always Claisen or?
Claisen or Diekmann. I'm putting ammonium chloride there. You can also H3O plus. He might write H3O plus there.
So just any acid.
In acid, yeah. The problem with H3O plus though, if you're forming an ester as a product, which you don't there, but in one of the other Claisens, it could hydrolyze to get a carboxylic acid.
This is one of the reactions where the last step is protonation, like final
Yeah.
protonation. And it's you have to make it relate with you deprotonate you deprotonate the one in the middle, and then you reprotonate with the NH4.
Yes, yeah. Or again, you could use just H3O plus, but I'm trying to be a little bit more precise.
It's not related, but it's not like the illid, right, or the PPH or whatever it's called, that like turns the carbonyl into the double bond.
Yeah, an illid will turn a carbonyl into an alkene. Do I have another hand? And since I am going through these quickly, and I have the problems posted, tomorrow, if you have time, I'd recommend going through them like with a blank copy, doing the problems, as well as going through your notes, doing those problems, making sure we don't miss anything. But because I am talking through so quickly, so you can get like a second try on some of these, because I didn't realize how long I made this. Okay, so we did the E1CB, we did that one. Okay, this one's a little bit weirder. This is sort of like a Michael addition. Heat in the first step, and then H3O plus, and water. Okay, so this morpholine, the nitrogen there, this is going to go there and do conjugate addition. There's the carbonate attack. So there's the conjugate addition. Then I'm going to protonate. Okay, there's this, and I already added the acid. But now we have two long mechanisms that we could write out, but we're not going to, for the hydrolysis of the aminium and the hydrolysis of the nitrile. So that will give us Isn't that fun?
So much
Very fun.
nitrogen, it's now all gone.
Huh?
So much nitrogen, and that's all gone.
Now it's all gone. And the oxygen we had is not there either. I made that one a little bit hard.
How does that go to that?
How does this go to this?
Yes.
So this part is the nitrile to carboxylic acid hydrolysis. That's like 11 or 12 steps or something.
Oh, yeah.
Oh, of course.
So that one's long. This is sort of like imine hydrolysis. You just attack here with water, protonate that, kick it off.
So if I just do H3O plus and H2O, it takes care of both of those things?
Yep. That one gets 3 arrows.
How do you like know that'll happen?
The hydrolysis part? Or in general?
Like, how do we'll go from those two things to that thing? Is that just like standard?
I mean, you could, well, this part you should know. I mean, this could add to some, it could add to MDK, like it could add to some other Michael acceptor. This part you should know. And it doesn't have to be this enamine with the morpholine either. It can just be a different enamine. Enamine, sorry, am I being a lot?
Wait, no.
Okay.
Anya's like drunk right now and she's like being really weird.
Really? Tell her to pull up, that'd be funny.
Bring some marks for Jake.
Sorry, that's funny. Anyways though, yes, enamine, you can do a conjugate addition, and then do hydrolysis. What? Did you say Jake? Oh. The enamine, because it's going to be a tertiary amine, that's where the ene part comes from, and that could do the conjugate addition, and that aminium will hydrolyze. Imagine you in August of this year just like listening to the last 2 minutes and none of those words.
I would have felt the same way as I do right now.
Well, I think it won't matter. At least I'm here right now.
I think you have a synthesis problem on your practice exam that has that first step. So look at that synthesis, and I can re-explain it at the end if you want.
We haven't done the Gabriel yet. Do we need to know the mechanism for that or no?
No. The more important part is just being familiar with it, maybe knowing what the nucleophile is. I think that might have been a practice problem. But knowing the steps of the Gabriel synthesis is not crucial. It was sort of just an example to show how the amines are synthesized.
That makes amines, right?
Yes. So I think you looked at that one and also Norlander, but those wouldn't really be tested on besides like potpourri probably. Okay, double box. Potpourri.
Yeah, why is it called that?
It's just like,
It's like just a little bit of everything.
I think that's what like it.
That's the actual word?
Potpourri? I think it's a French word, I
It
guess.
means a bit like everything.
Yeah, I don't speak French.
She said she's coming.
Is she actually drunk?
She's bringing fireballs everyone.
Get out. I can't condone this. On a Penn State Teams meeting being recorded,
There's no alcohol.
turn off the
Michael. She literally said Jakey, I'm coming.
Okay.
She said, I'm there, and I was like, yeah, sure.
It's okay, Jake. You're gonna be gone within like a few weeks, right?
Yeah.
So you don't have to worry about the consequences
But
of
no,
these
it's-
actions.
I think prison is
You're going to Berkeley.
well, I guess I'm not. I don't condone drinking at your young age.
She's
Oh
not.
my god.
Okay. You gotta lock this.
Oh, this is never gonna end. No, I mean, okay. Does anyone even know what an acyl azide is?
It's an amide with C2.
Okay, we're good on that.
It's an amide with C2.
Wait, is it not LEH?
Can you do
You
acyl
can't.
azides?
Yeah, to like.
What is it? Acyl Z.
Yeah.
Does it actually have to have a negative charge?
No, there's a, is it
That's just not being written.
An azide.
That's not gate, that's.
An azide is this N3 group.
Yeah.
You can also just write N3 if you want.
H3O.
What? What?
LEH. LEH does the reduction. Don't need to know the mechanism for it.
Yeah, because it's like a 47.
Is it?
Right?
Is it?
I thought it was.
There's no way it's 47.
Why is it not courteous? Courteous would give you the isocyanate.
And then you add the water.
And then you add the water and you wouldn't get this amine.
You need something.
You would get.
It's what you do.
I swear.
Of course.
No, God, of course. Are you serious?
Okay.
With the traditional way that we have to reduce it.
nitrile, what's it?
It's a
Don't
cyanide.
ask that. I stopped myself.
Oh, wait.
It's just
I just had a brain
LEH.
2L.
Just check. Just check.
Wait.
What? You don't need water here, no. I mean, not technically. You would add water, but when you do the mechanism, you don't use water.
If you don't specify that it's 2 LAH, is it?
It's only worth a point, so I'd give you the point.
Awesome.
Fire.
Okay.
I don't own my.
How do you make that?
Okay, two different ways to make a different amine from an aldehyde and a ketone. How do we make amines from aldehydes and ketones? That's an imine. Amine. We make with
What's normal?
reductive amination. I'm saying I'm going to give reductive amination a number 2 in order of importance for reactions on this exam. One is everything, all of the condensations,
That's fair.
which is like a lot of different reactions. Condensation chemistry, reductive amination. So from a ketone, so for reductive amination, where the nitrogen is, that's the oxygen of the carbonyl. So I'm going to take one of the other, so if this were an oxygen and a double bond, that's a ketone. If this were an oxygen and a double bond, that's an aldehyde. So here, the aldehyde, I'm going to draw it in the same orientation that it is in the final molecule.
So is it formaldehyde?
Yes, formaldehyde here.
Oh.
And then this is the ketone.
I see.
Those are the carbons. That is by, I'm going to need a bigger box. Yeah, Charles, right?
Wait, why does the aldehyde have 2 hydrogens on it?
Because it's formaldehyde, and this is only one carbon.
So where's the other carbon from?
What other carbon?
Wait, is there 2 hydrogens on that nitrogen? Am I right?
This is a hydrogen. This is an A, in reference to that's the A.
So where's the other?
Where's the other what?
Where's the carbon coming from?
This carbon? That's going to be our reagent. So that's the amine that we add to that one. we need pH 4.5. Methanol is the solvent. Sodium cyanoborohydride. And order of importance in terms of including things in the box, the amine and the sodium cyanoborohydride are definitely number one, sharing number one, because you need both of them. pH 4.5 and the methanol are just reaction conditions, less important, but still include them. Less important to write. You obviously need the conditions, but. And then the other side, we're just going to use the other amine, so we need to use this methylamine. Sodium cyanoborohydride. I'm writing out the word. pH 4.5. Methanol. Box is filled. Yes.
This is kind of hypothetical. Could you do just treat NH3 and just have?
No, because how would you get on both carbons? Well, yeah, you could say it would be more than one step though. You could do aldehyde, formaldehyde with ammonia in these conditions, semicolon, the same thing but with cyclohexanone. But that's 2 steps.
Okay. I mean, it doesn't really matter because you never remember that. But
You will remember this, yeah. You will. Reductive emanation.
Sure.
How are we feeling?
Better than
Jeez,
I know what you
Because you can't see his ears.
there is like there's like 2 mechanisms that
are really what?
it's like weird.
Weird?
Yeah, it's the third one
Yep.
and the 6th one.
Yeah. Okay.
Because the rest we kind of already touched on.
Since let's do mechanisms last since we've already done a lot of mechanisms. Let's do, and then I'll make sure that I'll do those ones. And I will go to 10:30 if I need to, and then you guys can just watch the recording if you need to leave. Watch the recording. Okay. Let's do the basicity ranking and the orbitals. So we have okay, so from least basic.
They know you're gonna show no, the next one.
Yeah. Yeah. I want the numbers. I don't have the numbers.
I have the number.
Do you?
Do you want it?
Yes, please.
Okay, how am
You need a Google Translate? It's in Spanish.
Where are the numbers?
What?
It helps me think.
I don't see numbers.
Do you see the letter next to like the Spanish PK Estas? Estas.
I'm just gonna give that back to you. Okay.
See how it is. No? I know like 4 words.
So,
I know my own.
I'll wait.
I'm sorry.
Yeah.
So, what is the pKa of guanidine, the conjugate acid pKa?
70.4.
No, it's not PKA.
Well, you don't need to know the number, but if you protonate it, that is highly resonance stabilized. We looked at that, right?
So it's
12.4?
It's the least basic.
Oh,
Most basic. Yeah.
Most basic, because it will willingly deprotonate. So A, most basic.
Yay. Oh, I got it wrong.
This amine amines are basic, right? That one you should know. Conjugate acid pKa around 9. That's a good reference point. Not resonance stabilized though. Going to be less basic. Less basic, yeah. A good thing to note as well when comparing between, say, this one and this one. We know first also that B is going to be the least basic because it loses aromaticity when it's protonated. So that's bad. We don't want to lose aromaticity. This one does not lose its aromaticity, but this lone pair is in an sp2 orbital. This lone pair is in an sp3 orbital. sp2 has more S character, which is going to be less basic.
Wait, can you explain the D thing again?
Why this one's here?
Yeah.
Compared to which?
I mean, you wrote it second, so I guess compared to A.
Yeah, so A we know is going to be basic because when it's protonated, it's highly resonance stabilized.
Yeah.
D is amines are basic, pKa around 9, and they have an sp3 lone pair as compared to C, which has an sp2 lone pair.
C's like sucking.
Yeah.
Yeah, that was still.
Yeah.
Yeah.
It's closer to the nucleus.
And they said
Okay. Now I have a question on here for what orbital are things in. This is sort of a random question. This lone pair is in which orbital? P, because it's aromatic. That lone pair needs to be in a p orbital in order to maintain the 4n plus 2 pi electron system.
Okay.
So this lone pair is in a p orbital.
SU2.
sp2.
What orbital do you know?
That one is not in a p orbital. That would put more electrons in E, but it's also just 3 electron domains, sp2. What? Okay, I made a mistake whenever I wrote this out. That should be a nitrogen there.
Oh, that makes more sense.
And this is in a
SP.
sp.
Would it be the same?
I did
Is
it.
it the same? If
What?
it was just a common?
Yeah. But I was looking at the nitrogen. This one is
P. Oh, SP2.
sp2.
Oh, so the other one.
Comparable to pyridine. This one is imidazole.
Yeah, I trust you wholeheartedly.
Because
I don't
Carolican's
trust
the
myself.
one that is that one with the 2.
I think it's imidazole. Let me look.
I have absolute faith, and it's not the purity.
We have to have those numbers.
I just know pyridine has a nitrogen.
In a normal rate, yeah.
Yeah, that's the
Yeah, that is imidazole. Not like
Is that the
super
one he was going to
important.
name his daughter?
The piperidine was listed on there. But he was also asking for like most stable conformation, which is a chair. That's the only one that's that. You know.
Yeah, aniline?
Aniline.
Aniline could be a good one to know as well.
Because it's an aromatic with a different end.
For just like what it is, what its name is, what it looks like.
I don't remember what it looks like.
It's a...
If it was in Spanish, it would help a little.
Yes.
Aniline.
He said he named his daughter after that.
You did, yeah.
He tried to. Wait, I think your name isn't her name like something different, like Margaret? Is it Rachel? I'm like 80-90% sure.
Okay. Synthesis.
There is a universe where
How many carbons do we have in the starting material? 6. How many do we have in the end? 5. What did we do? We formed a ring, right?
Yes, sir.
So we need to have some kind of condensation that forms a ring. These are carboxylic acids. What can we change them to make a condensation that forms a ring? What condensation forms a ring? Esters. How can we change carboxylic acids to esters?
Sodium.
What?
So you can do Fischer esterification. You could do diazomethane. Let's do Fischer esterification.
Oh, it's an acid?
Yep. If it goes in base, you deprotonate the acids and wouldn't go anywhere. Okay. We've made esters. Now how do we do Dieckmann?
OH, CH3OH, CH3O minus,
NH4Cl.
and then acid.
Yeah, all of what they said.
Bro. Didn't he say it out loud?
I said it's I said, oh, it's a synthesis. Okay, because I can't.
I have to try it.
Okay, we do the Dieckmann condensation, we get the 5-membered ring, ketoester, heat. Not just heat.
Water.
Acid.
Could you go over? How does it work with the methyl alcohol?
You do hydrolysis first. Turn this into a carboxylic acid. Then
Oh,
you
I
do
see. Then you.
Okay. This last part. So you have this ketoester. You have this ketoester. This becomes a carboxylic acid through hydrolysis with H3O plus. When you have the carboxylic acid that's on the alpha carbon to a different carbonyl, that's when you do the decarboxylation step.
Is that like CO2?
And then that
Yes.
goes away.
And then this just goes away
Okay.
as CO2. Yeah.
Can we go over that quickly, like after all this?
Yeah, we can do well, let's do that last part of the mechanism there. So the H3O plus and water makes a carboxylic acid.
One step.
And then the decarboxylation step makes an enol that you do tautomerization in acidic conditions.
What's the last step called for name for that?
This is decarboxylation. Yeah. You can do, if you add H3O plus in water, you can do decarboxylation with esters as long as it's like a beta keto ester. Or it could be a diester as well.
And just to make that carboxylic acid, the water acts as a nucleophile and attacks the...
Mm-hmm. Yeah, so you can either show this getting protonated and then attacked by water, or...
Okay.
Okay, we're moving.
Yeah.
Loving it.
Next, we got carboxylic acid to an amine.
Yeah. My favorite function.
Amines are your favorite function?
No, we use my favorite function.
Okay. I was gonna
An
say.
acid chloride.
You can use an acid chloride, I did not hear.
I think amines are like my.
Actually, you might not be able to use an acid chloride. I think you get an extra carbon.
What if you use an acid chloride?
Acid chloride. That's
Oh, I
not
think
good.
you get an extra comment.
I'm gonna start using acid chloride.
If you get excited about an acid chloride.
I can't do an acid
You can't do an acid chloride on that. He's right. You have to do the sodium azide.
Yeah.
Or the lame one with like sodium oxide. Oxide. Oxide?
Neon 2A. Methoxide. Anyway.
This is a one-step synthesis.
Wait. Oh, I think I made a mistake whenever I was making this, but I think you can still do this fine. Oh yeah, totally. Why did I do a carboxylic acid?
What?
Maybe I will go with an acid chloride.
What, can you?
Hey, Sato. Oh my god.
Because you do that, and then you do and then you do
Sodium azide.
sodium azide, and then
Oh yeah, so organic.
Bro knows his acid
I know acid.
He knows his acid.
I know acid chloride, I know nitro.
Well, I don't remember what I was gonna do. I didn't write it down. I think I was gonna do. Oh, I was gonna do DCC with ammonia,
What?
and then do Hoffman, and then do reductive amination. I like that better.
What?
Not because I'll do it both ways. I just like that better in terms of this is more steps.
It's 2 steps.
What?
No, it's gonna be.
Can we do like a semicolon? and
It's
then
gonna be
do
more
it?
steps than that.
Hey, I do think it's
Acid chloride.
Okay, DCC with ammonia.
Wait, what's the last one in the last one?
I erased it. I remembered what I wanted to do. Well, I was going to. Okay, you get the acyl azide. Just add heat to do. No, sorry. Yeah. Heat semicolon water to get this amine without that ethyl group, and then you do reductive amination with acetaldehyde. Anyways. It's essentially the same thing. The question is, are you going to use the Curtius rearrangement or the Hoffman rearrangement? But the Curtius rearrangement makes you do an extra step to turn this into turn that into an acid chloride. So there, you get this amine, and now you do reductive amination with. Huh?
Oh. You like make you react with
Absolutely brilliant.
These are the 2 carbons you add on from the acetaldehyde.
Wait. Hold on. Oh yeah, that, yeah, never mind. My bad.
What? Okay.
Instead of doing the Hoffman, can we do the other one with the sodium azide? And do it faster?
That's what that was the 4-step one. I was saying you could do either rearrangement, but the Curtius has an extra step to turn into an acid chloride.
It has an extra step.
Yep.
acid chloride to
Yeah, let's do whatever.
Then you do acid chloride, and then you
It's not fair.
Okay, we want to go from this ketoester to this ketone. Wait. You want to go from this ketoester to this ketone. Notice that we have a carbon here
This is bad, exactly.
that we don't necessarily have there.
I see.
Working backwards, we're going to do a decarboxylation.
Absolutely brilliant. Oh my god, I see it. The Holy Land.
You decarboxylate this ester. How do you get that extra carbon on there?
LAH and
Yeah.
Not LAH?
LDA, whatever.
Yeah.
Did you do a retro, retro, I guess it would be,
Like a retroclazen, maybe you're thinking?
yeah. But the problem, what I'm confused about with the retroclazen, it's the same.
But then you would get an ester.
Yeah, but then can't you just decarboxylate?
Not if you just have one ester. You need it to be a dicarbonyl. You need to have this to do decarboxylation. This though is, you can just use methoxide because it's a pKa of 11. And then how do we get the extra carbon? CH3I. Thank you, Kaylee. No, you can. Although LDA might also deprotonate over here.
If we did LDA, would we get credit for it?
Yeah. Again, the problem with LDA is that it could also deprotonate over there. Even though this is the more acidic proton, but when you use LDA, you tend to use it at really cold temperatures, and you can get dianions at that time.
Is acid and water just not like already gone back like
You need this carbon.
Oh.
Did you say something, Kaylee?
Why do you do the NaOCH3 and the NaOH?
This to deprotonate this, so that you can use that as a nucleophile for the synthesis.
Oh, so it's like all together, kind of. Like you like need that
Yeah.
to add the CH3I.
Yeah, I mean the semicolon's kind of.
Like if I just wrote like CH3I, like would that be wrong?
Yeah, because you needed something to deprotonate that.
Okay.
I'll leave the semicolon there. This one. John, do you have a question? You got it, bud.
I'll figure it out.
Yeah.
We will figure it out.
Do you think decarboxylation would be a mechanism?
Could be.
Okay.
Could
It's
be.
not that. It's not
It's kind of one step though, so maybe not.
that.
Was it?
I thought so.
Maybe it was, but it would be like a Fisher esterification kind of, and then the.
Like, yeah.
But it is a good one to know.
Oh yeah, it's right here.
Was it on there?
Yeah.
In what form?
It was.
Oh, that felt good.
It was the bomb.
Oh, it was.
Yeah, that's kind of crazy.
Wait, let me see it. Oh, that actually is true. That could be a good question because I forgot about the tautomerization as the second part.
Oh, yeah.
So. Okay, we're adding a lot of carbons. 4. Yeah. To a diketone. How we can't just get those on there by doing an SN2, right? Because if we try to do an SN2, well, you can't do an SN2 on a tertiary carbon. You could do a Novanagle.
Oh my god! Yes!
It's just against the double bond.
Methoxide, methanol, ketone, heat.
You know what? I'm calling it. It's gonna be cuprate.
Can we just get like 30 straight?
Then you can cuprate.
Why?
Conjugate addition, this is an enone. This is maybe the most chaotic review session we've had all year.
It's working. It's working.
It could get worse.
Is it working for?
I'm so tired.
I mean, this is the. I always figure we can do a little higher pace on this one since we had one on Sunday. You know. Well,
That didn't do much.
I feel like I learned from that.
Good?
okay. Well, we still have a ton of mechanisms. I'll do the highlights of the mechanisms. I'll leave the rest as an exercise for the reader.
It's an exercise to the research. Did you post the answers? Sorry, I may need them.
I'll think about it.
If I get this right, will you post the answers?
We'll just walk into the next 7 minutes and there's no thing.
That's clearly what's his name? Diekman? Never mind. I was kind of stupid. My bad. Okay. Clearly a Robinson.
If you have a Robinson annulation as your product, I highly recommend working backwards from that step because then you can decompose what your Michael donor and acceptor was. So in a Michael addition, we're forming this bond and this bond kind of because this is where the carbonyl was. So we need to have this, right? And if you count carbons, 1, 2, 3, 4, 5, 6, excluding this methyl, 6 carbons, 6 carbons, that's what we need to get to from there. The other thing that we add is the methyl vinyl, well, this one's not methyl vinyl ketone, but it's going to be everything over here in the form of a enone, like that, with methoxide, methanol, heat. We need to get that from this. How can we get that from this?
Is it one step to get there?
Yes.
So,
Yeah, I think it's two.
But I can't like, I don't do like.
Is it an internal alcohol now?
And then I don't know.
It's not a Dieckmann.
It's not a Dieckmann because a Dieckmann has the ester, just keeps the ester.
One ester.
You could do it in 2 steps.
I believe in internal alcohol. Actually, I changed my mind.
oh wait, it's because look at that oxygen.
We need to get rid of the oxygen. We're going to deprotonate over here, and then it's going to swing and attack that and kick out methoxide. I wouldn't use LDA.
What's your recommendation, sir?
I think just methoxide, but now I'm my.
Methoxide?
Yeah, just methoxide.
You're right. You're genius. My
Well,
bad for doubting.
you need an equivalent. Because this you generate as a dicarbonyl, that would get deprotonated again.
My bad, I doubted.
H2O plus, NH4Cl, whatever you want to write there.
Why do you need the H3O bonds?
To protonate the product, because this is acidic. Gets deprotonated by the methoxide, protonate with that.
Absolutely.
Do the whole thing, and then like you do it, and then you exit.
Then you deprotonate again and then protonate it.
What's this thing called?
This?
The first step.
First step,
That's just a Dieckmann.
I mean Dieckmann-esque. It's a condensation.
Okay.
Doing so.
Is that what you said, Sam? Did we say the same thing at the same time?
Yeah.
Okay, last synthesis, and then I'll go back and fill in the mechanism gaps. And then again, since we went so fast, I would recommend trying to go through these practice problems again, go through the practice exam again, go through your notes again.
That's a lot of going through.
Well, guess what?
That's like my DP professor's like, just memorize everything and get an exam.
Well, you will, you know? What can you say? Study until you're excited for the exam.
So excited for this exam.
I really hate that I did this question.
Why is there stereo specific?
That's no.
Great question. Why is it stereo specific?
SM2.
SM2.
Please, can we
Oh,
bring
this
this here?
does that. Wait.
Wait, I know this.
Wait,
Oh my god, you're making a pot.
would you do like LDA? No.
Or like not one.
Cuprate? Yes, but that's not there yet. Because we need to add this amine first.
Oh.
Or, well, last.
Yes.
That would be the last step.
That will be the step before. That'll be over here.
Clearly, ozonolysis and then reductive amination.
Okay, so we want this so that we can do the tandem bisphenol difunctionalization before that. With methyl cuprate. Quench with methyl iodide.
Oh, that's right. Yeah, that looks good.
And then this forward is 2 steps. First, ozonize in reductive conditions.
I knew it was not.
We did it, guys. We solved it. We cured cancer.
And then this is what?
H3O plus H2O.
Internal aldol with heat. So aldol C1.
Not acid.
OME, MEO is heat.
This is aldo E1CB.
Yeah. It's Ami and Mio and Heat.
Neo.
Is that not Mio?
Meow.
Oh, you're right.
Okay, and then how do we do this to this?
It's clearly reductive elimination. So methylamide, meow, H4.5, and then cyanide.
I call it home because I put it on the other side and it's home.
It's meow to
Wait,
me.
why did you use the LME and the
This is aldo E1sp. So you'll deprotonate here, make the enolate, attack this.
So when you use the H2O and H2O plus?
That's decarboxylation. That's if you have a diketo or a.
Oh, okay.
That's brilliant.
Well, this could also just be an ester, and then you use the H0 plus to hydrolyze that, and then do the decarboxylation.
Right. I'm just getting
Yeah.
What is considered the like
Your record,
It's a conjugate addition of a cuprate quenched with an alkyl halide to add on the second one, and you get this stereochemistry as a consequence.
I'm thinking it was something else. Wait, is this?
Okay, quad ammonium. Let's start with that since we didn't look at any examples of that.
What is quad ammonium?
We're gonna make a quad ammonium salt. I'll just do the one example. I hear the bell ringing. I don't know.
I hear the bell.
That bell's like totally.
Does he have a typo on there?
He would never.
Wait, was there something special? There were like horses there.
Oh yeah, there were horses. I was
We were there.
there were 2 horses in a cow. No, in a bowl. A bowl with horns. That with tennis balls.
Okay.
Oh, I see the vision.
Oh, we never did that. Where?
Oh, actually,
Wait, are you sure we did that? Very briefly.
I remember this now.
Never seen that in my life.
You definitely have.
What's this called?
Quaternary ammonium salts.
Oh, it's 5 carbons. You're so right. I forgot. Yeah, we went over this. Yes, we for sure did. I know
Reel it in, reel it in, reel it in. I know y'all be watching reels, but can we reel it in?
That's a neat slapper right there.
SN2. Kaylee, do you want to get up here and finish the mechanism?
No, I'm okay. I'll leave that to you. I'm gonna leave that to you. Leave it to the press.
Oh my god. Just keep going.
What you want, man? I don't care. Can we do one on 14? Can we do one on 18 so it's like Hama Toyo Koei? Bro.
You're speaking Spanish.
Okay. Now we have. This is the carbonate from potassium carbonate. Deprotonate the amine.
Yes.
Or the ammonium.
I'm definitely getting somewhere.
It's literally just 2 SN2s with an amine. Why is he so mad?
I'll try my best. If I ever get 100% on the mechanism of this exam, you can do a bad thing.
Shit is kind of big.
This is no, Jake can give me a.
Okay, next, just another backside attack. I don't care about the confirmation. There you go. Oh, okay.
See, it was very easy.
And then if there were other things on this, if there were other things particularly on the carbon chain, then this could be like a precursor for a Hofmann elimination. Remember, Hofmann is less substituted alkene that you form.
Yes, I remember that.
I understand the vision.
Just repeat everything. Sorry.
I'm fairly sure the average elementary schooler could have figured this out.
Chapter 1.
Oh, yeah.
Remember when you thought like
Hoffman. Okay.
Okay.
So that was the quad. Decarboxylation, I'm going to skip that mechanism. You said which ones are weird? 3, 3, and... Wait, isn't 6 just for decarboxylation?
Oh, yeah, it's been
Okay, 3 and... Everything else we've pretty much done.
Yeah.
So let's just do mechanism number 3. If you have questions about... Or maybe 2 we should do as well. 2 and 3, and then call it?
Yeah.
What's what? That's the Hofmann elimination.
Is that a mechanism over here?
The mechanism is just...
It's very simple.
Oh, that's just like a reaction.
This is solvable by...
Maybe I'd be like, oh.
Someone needs that. That's an easy name.
That's right.
I can solve that. It's methyl. Okay, give up.
There's a methyl or something.
1, 2, 3, 4, 5, 6, 7, 8. That's 9 carbons. There's a methyl. I see a beta keto ester.
Is there anything that isn't a carbon or a hydrogen?
Yes, there is.
Okay,
Thank you for all your hard work.
of course. Adios. All right, where do we... What's the step 1?
Deprotonate.
Deprotonate where, John?
The alpha carbon.
Of
The keto ester.
keto ester.
Brilliant.
I can't remember that.
No, there's 2 keto.
It does not matter where you draw the resonance structure because it's just a resonance structure.
Oh wait, from that side?
It does not matter where you draw it. This, you can draw it in a different conformation. For time's sake, I'm just going. Conjugate addition here. This will make the ring.
Crazy ring. Do we form the enolate on the ester or on the ketone? Because I feel like we form it on the ketone.
I think I missed a carbon in the problem.
Perhaps. Oh, it doesn't matter, my bad.
Yeah.
No, I'm fine. Oh, did you?
Oh, wait, yeah.
No, I was in the same boat as you. I was like, wait, no, yeah. Okay. Protonate. High energy organic chemistry.
Oh my god, we did it! That's it!
Okay, that's it. That's all you have to do.
Are you being serious or do you have to deprotonate again?
You have to deprotonate again.
Okay. Wait, Jesus.
Yeah.
So the timeline, that's like, you make your final product, then you gotta deprotonate it again, and then you get your final product. Actually,
Right here.
only when you have like a Claisen condensation.
Claisen, Dieckmann, whatever you want to call it. If you have 2 carbonyls.
2 carbonyls, but if it's like an aldol, you don't deprotonate.
No, you don't. Not for aldols. That's what this.
Wait, so if it's a diagram now?
Wait, I thought it was only for the semicolon one.
Did I put? Oh, because we. Wait, what?
I think you just semicolon one.
No, but I didn't put one equivalent here. Why did I not put one equivalent here?
I don't think you need just one equivalent. It's not like.
Wait, we lost. Let me think. Because we did that, did that. But we didn't kick out any. We didn't kick out any additional methoxide.
I hope you sleep well, Greg.
Oh, yeah. You come over, we're not sleeping.
I think, okay, this was, there is a similar one that was on a previous exam, but I think you just made a typo. I think.
What if it was one equivalent, then you had a depronate for it again?
That's what I mean. That's what I think, because it said catalytic on the previous exam.
So it says one equivalent, okay.
Because you do have the dicarbonyl you need to deprotonate.
I did hydronium.
Fine. Yes.
What hydrogen do you deprotonate?
This one right here, because this is the most acidic hydrogen. It's the one between the carbonyls.
Okay, I thought so. I just wasn't.
Yep, all good.
Oh my god, and then it happens. And then you form your favorite
I thought I was gonna have to remember the NH4CO. I was gonna remember that.
You gonna go to class?
And then we protonate with ammonium chloride. Okay. Yep, have a good one.
Jake, one
Yes.
more.
Yeah.
Does it matter which carbonyl you push the resonance onto?
Nope.
Okay, so I can put it in the ring?
No. You didn't. Oh, like right here?
Yeah.
Yep.
So you have to depronate and protonate together into one equivalent then?
Mhm.
Is that like the Schaffer
Yep.
rule? Okay.
Okay. The alkene is there, so we have an enamine, but for reductive amination, we need to have an aminium. So how can we turn this enamine into an aminium? Protonate the nitrogen?
Protonate the carbon, the beta alpha carbon. No, the
You're
you have a carbon.
on the right track. We're going to protonate the carbon, but with like resonance. So that,
Guys, that's the alpha.
And it's because that makes it more subject to double bond.
Oh, wait.
Yeah, that's the alpha carbon.
The carbon gamma to the nitrogen.
beta?
We don't call it.
You're putting the proton on this carbon. Beta.
Huh?
Alpha to the, I mean, it depends if you,
It's alpha to the carbon of the nitrogen. That's how we're supposed to do it.
anyways.
What? We don't call it beta to the nitrogen.
Guys,
Last step.
Top or bottom.
Okay, donate, oh my god. Donate the hydride,
and we're done.
and that's it. And we're done. That was the longest, but also not particularly much longer. That was just, we had a lot to do.
Thank you, Jay.
Thank you,
Thank you,
Jay.
Jay.
You're welcome.
Couldn't have done it without
Just
you.
have you session.
Well, we still have the exam tomorrow, so we'll see what you couldn't have done without me. Huh? I have, where are we at? I mean, with the ones of us that are still left. 1 to 5.
Not like a 2.
Better than none.
Like a 1.7.
This is higher than we're normally at, so that's good.
Yeah.
Okay, I'm gonna end the recording.
Really? I swear to God.